Okay, so from last week, what I would like for you to do, okay, is go ahead and do the bore model for, or no, yeah, the bore model for, let's go with copper, element 29. Any others about to fall? No. So, how many people are done already? Yep, that's right. It was well worth going. That's right. Overcomer. I can't see what that last number is. Nope, not quite. You got the right idea. Element 29. Now that we got it done, Begin when you feel ready. Okay, we got it done. Got it pretty well whipped. Okay, so if you are struggling with this, you're not doing yourself any favors if you just nodding your head yes, and we're not really understanding this. Okay, this is why. Okay, so when you did this inside the nucleus, we know there's 29 protons. Okay, so all these little numbers are going to add up to what? That you put around there for those of you who are done. 29. Okay, so you follow your slide rule. Go 1s2, 2s2, 2p6, right? You're following your slide. Then what comes next? 3s2, 3p, and then 4s2, and then finally, what column in the D block only is copper in? The ninth one. So that's where that last number comes from. Okay? One of the things we want you to look at, we're doing a little bit of looking ahead. In case you're wondering, why is it that we're doing 4s2, then 3d after that? Or 5s2, and then 4d? Or 6s2, and then 5d? I said that twice, didn't I? Okay? But why would we fill up the fourth energy, start filling the fourth energy level first before the third one's even finished? Well, there's a couple reasons. What makes that correction for you? It's on the paper in front of you that you probably used. How do you know that the fourth energy level starts to fill before the third one ends? Yeah, because your slide rule tells you that. But if you look at page 144, it's just a little bit of looking ahead on why that is the way it is. Okay, just follow along because we want you writing it this way because you're not going to understand these quantum numbers if you just follow along with the way the author writes these. Okay, we'll make sense of that in just a moment. Page 144. Okay, it says the D block elements. In other words, groups 3 through 12. Okay? So, it says for energy level N, that's going to be one of your quantum numbers. We'll get to that in just a moment. There are N possible sublevels, and so the D sublevel fills, or excuse me, so the D sublevel, God, I can't talk. Try this again. Okay. There are N possible sublevels, so the D sublevel appears when N equals 3. Okay? This 3D sublevel is slightly higher in energy than the 4S sublevel. So, these are filled in the order 4S, then 3D. And we know that because you're looking at your slide rule. It also makes that correction. Because if you look in different spots where this author is writing these configurations, they put 3D first instead of 4S just for convenience sake. But this is establishing the idea it takes less energy to start filling the fourth energy level, the S orbital, first, then the 3D subshells. Okay? Now that might not mean anything to you right now, but we will start applying that shortly. Okay, so what is a configuration that we remember from 2 years ago? Especially if you took a shortcut. Anyone remember why you would use a noble gas shortcut? Does that, maybe if you saw it, you could say, oh, I remember that. You need to pick the smaller noble gas than what you're dealing with. So if we're dealing with element 29, what would be the noble gas? It has to be smaller. So would you use argon or krypton? You'd use argon because that number is smaller. So if we're starting with an argon core, what element is argon? 18. So we're already establishing all these numbers are up to 18. And that's fine. This will make sense in just a moment if you bear with me. Okay? So find where argon is on the periodic table. What period is argon in? Gesundheit. That's the column. We want the period. It's in the third period. So now you can say what column in the third period is argon in. It's in the sixth. So that energy level is completely filled. So what that means is follow your slide rule and on your periodic table, what comes after 3p6? 4s2, okay? Then what? Okay, we're going to put 3d, and now, what column in the D block is copper in? The ninth one. So, if we add these exponents and 18, what do we get? No surprise, 29. So what a configuration is just a linear depiction of these elements, okay? So you can write these out longhand if you wanted to say, okay, we're doing element copper, okay? So we know it's element 29. You can follow your slide rule and say 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2, and then 3d9. If you add up all of those exponents, same thing, you get 29. 4, 10, 18, 20, 29. Now we went through that really, really fast. Is anyone lost right now? Okay? And one of the things that you can do to reinforce this is if we put argon's configuration, notice if we do that, we know that it would be 1s2, 2s2, 2p6, 3s2, 3d6. What do we notice about this and this right now? Stopping right there. Are they the same? Yes, that's the exact same thing. So when you put this in as a noble gas configuration, what you're saying is I'm going to take this, put argon up here, and then just deal with what we have left. Okay? Does that make sense? Now, we're going a lot faster than what we did 2 years ago in physical science. Because we're older, we're more mature, right? Okay? Good. Hopefully we can agree upon that. Okay. Anyone lost on why we use this noble gas configuration? Left outside, are we on the bus? Left outside. Left middle. Middle. Yes. Do they want to be stolen? Okay. So middle. Right middle. Right outside. Okay. So if you prefer doing this type of configuration, that's fine. But how many of you would agree that this is much simpler than all of that? Would you rather do the blue or the green? Would you rather do the blue? And I think you'll make the tendency of making a mistake would be less if you choose to do it that way. All right. So let's maybe try something a little different. Okay. And how about you pick an element, it'll be a little bigger, from, let's say, 81 to 85. 80. Okay, I didn't hear the second part. We actually did that already last Friday. Because it's bismuth, isn't it? I'm not even going to look at it. I bet you said 83. I don't even look down here. 83 is bismuth. Yeah, but that's fine. Now we're going to do the electron configuration. So now when you're looking at this, you say, man, if I'm going to do this longhand, I got to have 83 of them. That'll take you a while, but that's okay. But can you take a shortcut to this? Yes, which would mean, which noble gas would you select? Xenon, which means you are up to what number? What is xenon? So we got 54 here. Okay, so now the next thing you're going to want to do, what period is xenon in? The 5th period. So that means we take that period, and what block is xenon in? The D block, or excuse me, the P block, and what column is it in? Okay, so we take what you said, the 5th period, the P block, and the 6th. So that is already full. So what comes after 5P6? Okay, so now if we put 6S2, we still follow your slide rule. What comes after 6S2? Okay? Okay? All right, do we need to keep going? Yes, we do. You can always check to see where you're at. If we take 54 plus 2 gives you 56. 56 and 14 gives you what? 70? Okay, so we have 13 to go yet. So, what comes after 4F14? 5D10. Then what? So, right now, when you say 5D10, I bet that we are up to mercury. Okay, I'm willing to bet this would add up to 80. Well, let's check. Well, we said this was 70. 10 more gives you 80. 54, 56, 70, 80. So we can make some predictions and say we got 3 left to go. But your slide rule will tell you that. What comes after 5D10? 6P3. And why is that 3 correct? What column in the P block is bismuth in? 3rd one. So if you add all these numbers together, 54, 56, 70, 80, 83, that matches what bismuth was supposed to be. Okay? So are we good with these configurations? Left outside, left middle, middle, right middle, and right outside, and right outside, and right outside. Okay. Now, as we look back to page 107, okay? Please turn to page 107. So atomic orbitals and quantum numbers. Okay, so on page 107, okay, in the Bohr atomic model, electrons of increasing energy occupy orbits further and further from the nucleus. According to the Schrödinger equation, electrons in atomic orbitals also have quantized energies. An electron's energy level is not the only characteristic of an orbital that is indicated by solving the Schrödinger equation. So, in order to completely describe orbitals, scientists use quantum numbers, and that's what we're going to be dealing with the rest of this time. And the paper that will be handed to you will have the quantum numbers on there. Specify the properties of atomic orbitals and the properties of electrons in orbitals. Okay? The first three quantum numbers result from solutions to the Schrödinger equation. They indicate the main energy level, the shape, and the orientation of the orbital, of an orbital. The fourth, the spin quantum number, describes the fundamental state of the electron that occupies that orbital. Okay, so I think the best way to do this is see an example on what these quantum numbers are, then come back to it and see what it says about what these principal quantum numbers are supposed to be. So, we're going to refer back to copper, okay? Because remember, that had this. We had argon, and then that was what? 4s2, 3d9, okay? So what that means, okay? Turn over to page 108. And at table 1, table 1 is telling you orbital letter designations according to the values of L. Now that doesn't mean anything to you right now, but it will here shortly. Okay? So these are your four quantum numbers. We've got N, these are the variables. And we've got L, we've got M, and we've got S. Okay. So that we have to do the orbital diagram first. So what you can do is take a shortcut with this and see, okay, these last electrons went into the third energy level, the d orbital, and for instance the ninth column in that orbital. Okay? So each horizontal line that we're about to draw can hold 2 electrons. Okay? So if the maximum that the D block can hold is 10, and each horizontal line can hold 2, we take 10, divide that by 2, and how many horizontal lines would that be? It would be 5. Okay? So what that means is we're going to put 5 horizontal lines. And underneath, we're going to put 3D down here. Okay? So now we go back to where these last electrons went into, which was the third energy level and the d orbital. Now what you're going to do is start putting some of these arrows in, and that denotes what these electrons are, because there's 9 of them. Did we just pull this 9 out of the air, or where's that coming from? The number 9. Where do we see the number 9? Right here. Okay? So we're going to put 9 of them in there, and we do them one at a time. 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, we want it to look just like that. Okay, and then we're going to circle this guy right here, because that was the very last electron. Okay? So N is a variable for the energy level that last electron went into. So that energy level is what? 3. So N is 3. So now when we look at page 108, it says orbital letter designation according to values of L. Well, here's our L. The block that electron fell into was D. So looking at table 1, when we find the letter D, okay, we're looking at this right here. When we see this right here, letter D, what value does that have given to it? The number 2. We're not just making that up. That number is assigned to it because it fell in the D block. So this, therefore, is 2. Okay? Now, what we want to do, the letter M can be this. M equals a value of negative L to positive L without skipping over 0. So what that means, if we start at a value for negative 2, this is where these numbers come from. Since L we had given as 2, it can be a negative 2. So negative 2, negative 1, without skipping over 0, plus 1, and plus 2. So we put a circle around that electron. So the number underneath that must be the value for letter L. And that would be which one? What value is, which value is M of all of these? Where's the last electron? Plus 1. Okay? So that's where that number comes from. And then finally, the S, or the spin, if it's got a positive value, we say thumbs up. If it has a negative value, we say thumbs down. So this last electron then is pointing down. So what do you suppose is more negative? Or what would we associate that with? Positive, or which is going to give you a negative reaction? This or that? That. We say thumbs down. So if that is pointing down, and you say that's a negative reaction, which would be correct, this therefore is negative 1/2. Okay? Who's lost? I would expect some hands to go up because this is, again, brand new information. Okay? So now that we've seen an example, now let's go through and read it. So now you can see how this kind of pertains to how we came up with these numbers. Okay, so back up one page, 107. The principal quantum number, okay? It says, the principal quantum number symbolized by N indicates the main energy level occupied by the electron. So the main energy level through all of this is where the last one fell. Here is your main energy level right there. That's why N equals 3. It's not always going to be 3. It could be 2, not in this case. But different elements are going to give you different numbers. I think you would agree that would make sense. So do we see why we're getting 3 for N? It comes from this right here, or this right here, whichever you feel more comfortable with applying that to. Okay? Values of N are positive integers, only 1, 2, 3, and so on. As N increases, the electron's energy and its average distance from the nucleus also increases. Okay? So we don't need to go any further with that. Okay. Now, angular momentum. Okay? Except at the first energy level, orbitals at different shapes known as sublevels, I always say subshells, sublevels, okay, known as sublevels, exist for a given value of N. The angular momentum, The angular momentum quantum number symbolized by L indicates the shape of the orbital. For a specific main energy level, the number of orbital shapes possible is equal to n. The values of L are allowed are 0 and all positive integers less than or equal to n minus 1. And that's kind of where that 3D comes from, but we're not going to spend that much time on that to go that far in depth. For example, orbitals for which n equals 2 can have a value of two shapes. L equals 0 and 1. Okay? So I think we're going to go through and do another example, maybe just a little bit smaller, so we can see where these values are coming from. Because like I said, I would expect that some of you are looking at this and say, I don't have a clue to what's going on. Okay? So let's maybe look at something that's a little smaller. So how about you look at element 5 to 9. Pick one. Okay, so 4 then is not going to be in our range. 5 to 9. Okay, so element 6 is carbon. Okay. So I don't think we need to do a shortcut for that. So now, since we're going to do carbon, we're going to do the orbital diagram. 1s2, so up, down. 2s2. Okay, now the p block can hold how many? 6. So if we divide that by 2, how many horizontal lines would that be? Okay? So 2p. Now, what column in the second energy level and p block is carbon in? Just the p block only. Okay? So therefore, we do 1 and 2. How many arrows do we see total? What's the atomic number for carbon? Okay, so we got the correct number of electrons denoted by arrows, and we've got the correct denotation up here. So, as we look at this, okay, these here, okay, so if we were going to do a quick Bohr model, which would not take long, because we're only dealing with 6 electrons, okay, we got 6 protons in the nucleus. We do 1s2, 2s2. It would be 2p6, but that's where these numbers are coming from, right here, from the Bohr model. Now, if we do a configuration for this, what's the linear depiction? 1s2, comma, and then 2p what? Not 6, 2. Okay? Now, if we were to do an orbital diagram, that's what this information is. We say that the s block can hold 2, and if it can hold 2, and we divide 2 by 2, it gives you what? 1, and that's why there's only one horizontal line here. The s block can hold 2. Okay, so if we divide 2 by 2, it gives us 1. The p block can hold 6. 6 divided by 3, 6 divided by 2 gives you 3. That's where those horizontal lines are coming in. Okay, so Bohr model, we understand this, right? Okay, electron configuration, do we understand that? Left outside, left middle, okay, middle, okay, right middle, right outside. Okay, so Bohr model, the configuration. Here we have your orbital diagram. This information comes from the configuration. The orbital diagram, this here, comes from the configuration. So do we see where these numbers, these arrows are denoting the electrons? That's the only difference that there is. Yes? No? Okay. All right. We're going to do boron now. Element number 5. Okay? So how would we do boron then? Okay? Follow your slide rule. 1s2, 2s, and p. I'm just going to put an E there because it's just easier to see the E as opposed to trying to put a number 1 on there. So letters and numbers all add up to 5. Okay? Bohr model. Now, if we're going to do a configuration for that, we just do the linear depiction. Okay? The first energy level, S block, can hold how many? Okay? Second energy level, S block, can hold how many? Okay? Now, for the second energy level, the P block, it can hold how many? 6, but how many do we put in there? 1. Okay? So we would agree that those two are the same exact content or information, just a Bohr model and a configuration. Do we agree? Yes? So all you're doing is taking this information from this electron configuration and putting it into another horizontal depiction of the electrons pointing up and down for your quantum numbers. So if we take this and move it over here and say 1s, and it can hold how many? 2. So the arrows are the electrons. So we start by pointing up and then down, because each horizontal line can only hold a maximum of 2. Okay, so we've taken care of this one. Now, how do we do this? Well, let's move it over here. Okay, 2s, and it can hold a maximum of how many? 2. Well, here's our 2 right here. 1, 2. Now, the P block can hold how many? Can hold 6. And if we have to divide them by 2, that gives us how many horizontal lines? Okay, so 3. So 2 and P. Okay, and how many arrows would that get? Just 1, because there it is right there. Okay, so all 3 of these are showing a number of 5. It's just the quantum numbers is going to be just a little bit different on what you're illustrating. Okay, so do we understand the orbital diagrams? Just yes. Okay, because we know that this block, it can hold 6, right? And each one of these horizontal lines can just hold a maximum of 2, right? So therefore, that means you can only have 3 horizontal lines. You're just dividing how many it can hold by how many, by 2. Because if it could hold, like the F block can hold how many? 14. So how many horizontal lines would that be? That would be 7. Yeah, so you'd have to draw those 7 out. Even if you don't use them, like right here. We're not using these 2 subshells in this orbital, but we still put them in there. Okay, we're going to tackle the quantum numbers again. what is the main energy level for boron that that last electron fell into? And that comes from this right here. Okay? So N is 2. L is a given value on page 108. And that value, say again, is, okay? Is anyone lost with where these two numbers are coming from? Left outside. Are we good? Left middle. 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 Are we good with where these two numbers came from? Okay? Page 108. When you look at table 1, okay, we find the letter P because it fell in the P block here. So that means that the given value for L is what according to table 1? Okay, so yeah, 1. And that's why we put that number there. So it's a given value. Okay? Now, since this has a value of 1, this has to be a value of whatever whatever value L was to a positive value of what L could be. So if we say it's 1, it could be -1 by putting 1 in for L. That's all we're doing, showing here. Because L is just a variable. Okay? So we put 1 in without skipping over 0 to a positive value of whatever L could be. Okay? And we take this information and we put it up here and say, now we're going to figure out what M is. So it's either -1, 0, or +1. So that last electron fell in which one of those subshells? What value? -1. There it is, right here, and that's where that value comes from. And then finally, is this a thumbs up or a thumbs down? That last one. So that's a positive reaction then. So S, positive or -1/2? +1/2. One, 2, or 3. So since it fell in the P block, you look at table 1 on page 108 and it says it has to be what value? 1. It tells you that on that table. Then we put those values in for L and say -1 to 0 to +1. So do we understand how we get M? Where M comes from? Left outside, are we good? Left middle, middle, right middle, right outside. Bring back good memories, Mr. Hoth? This is just like riding a bike. Now we know, oh, I remember this from college. Okay? It's not I'm going to pass out a couple of these papers. These are due on Thursday. Okay? Today's only Monday. Okay? So, what we can do, okay, I'll go ahead and pass these out. And you can even pick one. We're going to have to be really, really fast. Yep. Yep, 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 yep. We aim to please. Yes. Okay. Did you get a copy? Okay. There's one. Okay. And then. Okay. All right. We'll start working on these tomorrow. Won't get a chance to get these to you yet. So. Okay. Have any problems? Get in and talk to me, please. All right. We'll catch up with you next time.